We are glad to present our new research, geometry-based hand-eye calibration. We'll also explore its applications in robot-assisted medical procedures. In summary, this work introduces a novel hand-eye calibration method that does not use the conventional AX equals XB or AX equals ZB formulation. It solely uses the geometry of the end effector and is repeatable and accurate. Robotic systems are becoming more prevalent in medical and surgical fields. These advanced robots can execute tasks with accuracy and consistency that surpasses human ability and enhances overall procedural safety. Enhanced by mechanical accuracy and machine perception of the surroundings. Robots can perform tasks that require a high level of dexterity and stability while improving safety by defining forbidden zones and virtual fixtures. A prerequisite for using such improvements by robot-assisted processes is obtaining the missing transformations along the kinematics chains of the involved equipment. The hand-eye calibration problem is a crucial problem for solving the transformation between a sensor and the end effector of a robotic arm. Typically, this calibration is critical when dealing with setups that include a passive sensor such as a rigid body marker with retroreflective elements or an active sensor like a tracking camera. The goal for both scenarios is to precisely define the transformation linking the sensor to the center of the end effector. Transcranial magnetic stimulation, TMS, is one of our motivating medical applications. TMS is a non-invasive technique for brain modulation by applying magnetic fields to stimulate nerve cells in the brain. It has diverse clinical and research applications including neuropsychiatry, neurology, and cognitive neuroscience. Commonly, TMS coils are positioned on the subject's head by human operators relying on neuronavigation systems for manual alignment. The accuracy of manual coil placement largely depends on the operator, with an average error ranging 5 to 6 mm. Robot-assisted TMS can address this limitation by improving the accuracy of TMS coil placement on the head. Robotic TMS relies on an optical tracking camera to obtain the poses of the subject's head and the TMS coil. Thus, hand-eye calibration is required. TMS serves as an example of a non-invasive procedure. On the other hand, robotic femoroplasty represents an invasive application. Minimally invasive osteoporotic hip augmentation is a procedure to inject bone cement into the femoral neck and head, which reduces the risk of hip fracture. The tool of the robotic system is a custom-designed robotic drilling and injection device. Similar to TMS, femoroplasty also requires an optical tracking system to obtain the poses. The conventional mathematical frameworks for hand-eye calibration are primarily based on two formulations, AX equals XB and AX equals ZB. Both of them require a repeated process where the robot is moved through various joint angles to accumulate a dataset of poses. Most methods reported in the literature solve AX equals XB or AX equals ZB by modifying data collection and regression process. These methods treat the robot as a sensor. Optical tracking cameras are typically considered to be accurate. However, it is challenging to achieve the same level of accuracy with most robots. Errors can arise not only from the robot's actuation but also from suboptimal fixation. Theoretically, the transformation between a sensor and an end effector is purely a geometric relationship, constant and independent of the robot's position within its workspace. The fundamental concept of our work is to only trust reliable optical tracking cameras for data collection and use geometry to infer the transformation between the end effector and the marker. By eliminating data collection based on robot poses, the calibration method becomes independent of the robot poses and workspace considerations. For a practical demonstration, we design an end effector attachment. The attachment connects the flange of the robot and the TMS coil. The end effector attachment we've developed has identifiable landmarks. The precise locations of these landmarks are determinable from the CAD file. In our design, the landmarks are specifically made as grooves forming multiple straight lines. The groove design enables us to digitize the landmarks easily. It also enables us to perform error reduction by regressing a line and resample landmarks from those lines. As shown, the origin of this attachment coincides with the center of the end effector. The digitization generates the point cloud in the sensor's reference frame, and the coordinates of the landmarks from the CAD file are in the end effector's reference frame. Thus, we can simply perform a pair-point registration algorithm to obtain the missing transformation. Most robot arms are equipped with a circular flange, and we can exploit this property of the circle. Although we assume a circular shape here, the method can be generalized to other geometries. To demonstrate, we provide an asymmetrical example in femoroplasty. In this example, the attachment features for discrete points as landmarks. While grooves have not been incorporated into this design, they can be added to facilitate the digitization process or to minimize errors in landmark localization should such needs arise. To this end, we summarize three conditions for a successful GBEC use case. 1. The end effector attachment has identifiable and digitizable landmarks. 2. The end effector, or robot flange, center can align with a point whose relative location is geometrically derivable by the landmarks on the end effector. 3. The landmarks on the end effector attachment need to be visible by the sensor to be calibrated. We examine the accuracy of the calibration for robot-assisted TMS by decomposing the sources of errors and investigating them from lower level to higher level along the propagation of the errors. 57 calibrations are repeated. The error of determining the positions of the landmarks is called fiducial localization error, corresponding to the errors during the digitization process by touching physical landmarks using a tracked probe. Pre-FLE is the distance from the ground truth to the digitized point cloud, whilst post-FLE is the distances from the ground truth to the projection of the digitized point cloud on the regress straight lines. As shown from our results, the mean of pre-correction FLE all reduced and the mean percentage of correction is up to 13%. We also demonstrate whether our method is dependent on the workspace of the robot. In this figure, the transformations derived by Gbec and AXXB at 3 different robot workspaces. The transformations are visualized as vectors using the position to represent translation and direction to represent rotation. The compactness of the vectors represents repeatability. At each workspace we performed 8 Gbec and 13 AXXB calibrations and obtained the resulting transformations. The cluster in Gbec is tightly distributed within a range of 2 mm in all axes. The previous results is also consistent with the repeatability shown in this figure. Gbec outperforms AXXB in terms of the standard deviation of the results of the calibration in axes of both rotation and translation. We performed alignments using the calibrated tools for both robot-assisted TMS and femoroplasty on an integrated medical robotic system and investigate the error between the target pose and measured pose of the tools after alignment. A laser-scanned foam head and a femur phantom with a CT scan were used in the experiments, and the registration residual for both were less than 1.5 mm. The table shows the mean and the standard deviation of the translational errors and rotational errors in 12 alignments for each application. In this work we introduced Gbec, a hand-eye calibration method that leverages the geometric features of the robot flange and its attached marker. Our experimental results demonstrate that Gbec is accurate, repeatable, independent of workspace or robot pose, and only rely on the geometry of the end effector attachment. We extend the method to accommodate both symmetrically and asymmetrically placed landmarks on the end effector, making it applicable in various applications such as robot-assisted TMS and femoroplasty.